evening everyone. A warm welcome to the 44th annual meeting of Astronomical Society of India hosted here at IIT Guwahati. It's truly a matter of pride and privilege for IIT Guwahati to organize this prestigious gathering. So now we will begin with the public lecture session, and I would like to invite Professor Divya Oberoi from NCRA to host this session.
Good evening everyone, and thanks for joining us for this public lecture. And as this is a public lecture, let me start by saying a few things about the Astronomical Society of India. Right? So the Astronomical Society of India was established in 1972, and it is the prime association of professional astronomers in the country. We have now grown to include a little more than 1,000 members. And the objectives of the society, as you would imagine, are to essentially promote astronomy and related branches of science in India. And not only professional astronomy, we also work towards promoting science and scientific temper. And we organize scientific meetings and support popularization of astronomy and allied activities. A lot of that work is carried out by the Public Outreach and Education Committee of the Astronomical Society of India, of which I happen to be the chair. There is also a working group on gender equity, which works towards that aspect in the astronomy community. The flagship event of the ASI is the annual meeting of the Astronomical Society of India. Right? And it is the 44th one, which is being held here at IIT Guwahati, and we really thank IIT Guwahati for hosting us here. And a key part of every ASI meeting is the public lecture, which is always given by an accomplished member of the Indian astronomy community. And it is indeed regarded an honor to be invited to present a talk, the public talk at the ASI. And it is now my pleasure and privilege and honor to introduce to you Professor Annapurni Subramaniam, who is going to be our speaker today. So Professor Annapurni comes from a family of accomplished musicians. She is the daughter and disciple of the veteran Carnatic vocalist Shri Palakkad K.S. Narayan Swami. Her mother, Srimati R. Ramani, was a professor of vocal Carnatic music here. And she has often accompanied her father and guru with her violin complementing his majestic vocals, and her love for all things musical is evident in the sweet intonation of the instrument. And if you're wondering if I'm reading from the wrong CV, that's not the case. Okay. So Professor Annapurni serves currently as the director of Indian Institute of Astrophysics in Bangalore. Comparatively recently, in 2024, she was awarded the Rashtriya Vigyan Puraskar, Vigyan Shri, for space science and technology. She has about 3 decades of experience in research in astronomy and astrophysics. Over this period, she has published more than 200 papers in refereed journals. And during the course of this work, she has trained a large number of students. She has supervised 15 theses, and many other PhD students have worked with her for their thesis. She was the chief editor of the Journal of Astronomy and Astrophysics for a period of 5 years, from 2019 to 24. She is currently the scientific editor of Research in Astronomy and Astrophysics, which is published by the Chinese Academy of Sciences. She heads the membership committee of the IAU, the International Astronomical Union, and she has been involved in various space missions, including AstroSat, which she will talk to us about, and more recently Auditorium as well. She has contributed to the 30-meter telescope, which is being built by an international consortium, and India is among the partner countries. She's also the PI, the principal investigator of the proposed next-generation UV and optical space telescope, which goes by the name INSIST, which essentially leverages her experience from both AstroSat and UVIT. She has numerous awards and fellowships to her name. To give you an abbreviated list, she is a fellow of the Indian Academy of Science, a fellow of the National Academy of Sciences, and she has had these fellowships for more than a decade. Last year, she was chosen to be an INSA Woman Associate. She is, of course, a life member of the Astronomical Society of India and also of the International Astronomical Union. She is an alumni of the Kavli Frontiers of Science, which is instituted by Kavli Foundation and the National Academy of Sciences of the USA. She's a recipient of the C.V. Raman Young Scientist Medal for Physical Sciences, instituted by the Government of Karnataka. Served Power Fellowship, Nasi Bhuti Foundation Lecture Award, among the top 100 women achievers from India, chosen by India Today, Devi Awardee by the New Indian Express, Future Forward Female Award from CNBC News 18, and multiple others. Her research interests include star clusters, classical B stars, young stellar objects, blue straggler stars, the Magellanic Clouds, as well as other nearby galaxies, and her primary tool has been UV astronomy for studying these objects. What she's going to talk to us about is AstroSat. AstroSat was India's first space observatory, which was launched about 10 years ago, and it's unique in its ability to observe the universe in ultraviolet to soft and hard X-rays simultaneously. And with that, I invite Professor Annapurni to present her public lecture today. Let's all welcome her to the stage.
I thank the Astronomical Society of India, SOC, and the PAC for giving me a chance to talk to you. So when I prepared this public talk, it was supposedly for people who are new to astronomy, but I think we have a group of people who are familiar with astronomy and also new to astronomy, so I'll try to bridge the gap and keep it interesting for both the parties here. But I'm supposed to talk about a decade of AstroSat, India's first space observatory. You can see the picture of AstroSat here. I'm sorry. Picture of AstroSat here, also in the next slide. So, what I plan to do is to give you a kind of introduction to why do we need observatories, and what is the kind of landscape, and how do we do astronomy these days, and how AstroSat is extremely important, and how it has played a role. And I also give you a glimpse of, since I belong to a generation which was very fortunate to actually see the making of UVIT. I mean, I was part of UVIT. So how it was made, how it was launched, and the initial phases of getting it calibrated and make the science results, and also see the 10 years of it. So I don't think many generations have been able to do that. Now that we have done it, now what next is also I'll try to do at the end, towards the end. So moving on, so this is the AstroSat the entirety. So AstroSat has various payloads, and it was launched by ISRO in the PSLV C30. And this is the picture from one of the instruments which we were working on, UV imaging telescope. And you can see the picture, which is a combined image from the near UV and the far UV channels together. And this is a picture of a globular cluster. And I would like to iterate one thing. When we see the picture of the globular cluster in optical, you see a big patch, a lot of crowding, and you don't see anything through. But in this picture, you can see the kind of things behind the globular cluster. So there are some UV galaxies you can see over here. So two things it tells us. The resolution is very good. You can actually resolve even galaxies like, you know, these kind of corner galaxies where you can see the universe where stars actually collide. So what happens when stars collide, what kind of a population you get, what kind of crazy things happen over there, and what will be the end product when stars collide. If you want to see them, that is the only place. And even with this reasonable resolution, you're able to resolve it over here. So that was extremely good, and the UVIT and the rest of the instruments over here do stand as one of the important contributions and scientifically extremely productive instrument up in space, completed 10 years as such. So I just want to give you an introduction to my institute, that is Institute of Astrophysics. It traces its origin back to 1786 when an observatory was set up in Madras. So then it moved to a permanent building in Nungambakam in 1792, and then it operated there till 1899. In 1899, it moved to Kodaikanal. From Kodaikanal, there were a lot of work done, and then it became Institute of Astrophysics in 1971. And it moved to Bangalore, as the headquarters moved to here. Till then, it was actually Kodaikanal. And then we completed 50 years under the name IIA in 2020. And we have several ground-based stations listed out here. We are also building a planetarium in Mysuru under the name Cosmos. Will start operation in a couple of months from now. It will be one of the field stations of IIA. Apart from that, we also have two instruments. One is UVIT, like IIA was a major player in it along with other institutions, and we have the payload operation center of UVIT at IIA. And the coronagraph VLC on Aditya L1 is also delivered by IIA, and we have the POC. And these are two major payload which has been operated by ISRO now. And AstroSat seems to be has already completed 10 years, and this is into its third year now. So these are two major observatories which are being operated by ISRO, and I has been part of it, and I also have been part of the India TMT consortium for bigger telescopes. So moving forward, as you can see, we have ground-based observatories as well as space-based observatories. Now, what is the landscape looking like? We do need both ground and space. The space is not just that you get better seeing and better images. It is actually that some of the wavelengths get cut off. So if you want to actually study the multi-wavelength astronomy or understand a physical process by looking at photons generated at all wavelengths and then understand what is the physical process going on, you need to actually measure all the photons. If you want to catch all the photons across the wavelength, you must have your instrument above the atmosphere where this wavelength range it is blocked. You can see this is the wavelength range where it is transparency is there and some part of near infrared, and then it actually completely blocked, the radio is completely clear. So if you want to cover from gamma ray to radio, you must have a combination of the ground-based as well as space-based. Now there are challenges to have space-based because you need to operate them up in space, and ground also you must have them in good locations as observatories, and at the ground you also have to be the astronomical seeing and correct for it as well. So, but on the other, if you want to put big telescopes up in the down ground, it's fine, and you can also operate them for a very long time because we know that some of the telescopes like the 1 meter in Kavalur and the 1 meter in Nainital both have crossed 50 years. And we have been operating the Kodaikanal Observatory for 125 years. So you can actually upgrade them and use the same instrument and continue to be functional. But in space it's not possible, except the Hubble Space Telescope. We can't actually go and do a repair and upgrade, so they are for a fixed amount of time. And it's got a lot of challenge. If you forget a screw and that it actually, entire instrument can go into trouble. So you may lose the entire instrument up in space if you are not extremely careful. So the risk is too huge, and also the cost is huge. So you must have an optimized combination of your assets up in space as well as in ground to combine the astronomy photons across the wavelength, and you have access to everything, but at the same time you have to balance the cost and the long-term sustainability. Moving forward, if you look at the international scene, I took it from a NASA website, so they cover the entire gamma ray to radio by using ground-based as well as space-based observatories. Now this is the coverage internationally. Now when we started off with AstroSat, the wish is to combine from here to visible in one observatory, one telescope, one mission. So that is AstroSat. You can see multiple of them doing it, not that they have very specific objectives up in space, but here the AstroSat's objective was to cover the wavelength range with 5 instruments so that you can look at any part of the sky together in entire wavelength range. That was the idea. And ground-based here you can see from the radio to HESS, which is a gamma ray Cherenkov telescope. So we do have similar coverage of wavelength up in the ground, particularly from Hanley itself you can see, and combined with GMRT. So this wavelength range is covered, but we have different types of combinations. So in space we don't have too many of them, but this AstroSat is actually fitted in this particular module. So this is covered by these many instruments. We have the LAX-PC, which is covering the timing in the low resolution spectral studies from 2 to 80 keV band. So the LAX-PC is sitting here, the red boxes over there. And then we have CZTI, which is sitting over here behind this pink blocking thing. And then soft X-ray telescope is the single tube here, and scanning X-ray monitor is 3 of them here, and then the UV telescope is the 2 yellow tubes out here. Now this mission also brought together several institutions, astronomy institutions in the country, and worked with ISRO. So you can see that ISRO. So you can see that many of them here also have partnership with CSA and University of Leicester. So all these institutions work together to actually accomplish this particular mission. So I have a small video of making of UVIT. So I will be giving you a glimpse of how UVIT was made and what were the challenges through this video, because I had a first-hand view to it. So this is So this was made as part of 10 years of UVIT at IIA. So this was integrated at the MGK Menon Space Laboratory located at Hosakote campus. This building is there. So this is the assembled UVIT at MGK Menon Space Lab. So this is, and you can see the date, 2010-2014. That was when it was delivered to ISRO. These are the cleaning process because it's a UV. You can't have any contamination, molecular contamination, and that has to be cleaned. So any component going there has to be baked or cleaned. So you need to develop a baking mechanism, cleaning mechanism, and also the entire lab has to be monitored for contamination. So this is contamination check using UV lamps and bright lamps. And each components are baked, so all these accessibles like handling equipments and baking chambers were locally developed. You can see so many handling equipments. And the detector module is also integrated there. This is the inside the detector, and this is the detector module being integrated. 3 detectors, identical detectors went into it. So high voltage units, they're also checked, and this is the thermal control because it has to be the inside. To get a good PSF, it has to be thermally controlled. So some part you need to heat, some people, it's cold out there. So these are the collimator for testing the optics. So this is the mirror, primary mirror, and the coupons, they are made by LEOS, ISRO LEOS. And the assembly testing for the primary mirror. The primary mirror is mounted now. And this is the secondary mirror on the Spider. This is also produced by several industries, and all the testing and integration is done in the lab. So this is the secondary mirror integration. So everything has to be collimated, checked for optical alignment, and then put in. So these are integration. This is the filter wheel. So these are done in 2012. So the high voltage unit integration. So this is the integrated individual telescope. It's a twin telescope, one for far UV and one for near UV. And so these are the people, and these PPVs, the personal protection equipments, PPEs, were used much before COVID in the lab. So these were constantly in use. That is to actually make sure that you don't have any contamination which is there. And the assembled UVIT in class 100, and purging, dry energy purging to make sure that any contamination is there, it is flushed out. So all these protocols were made and maintained. and this is the vacuum flange for thermovac test. And it has to, when you have to take it to ISRO, also the packing UV loading container we have to design and make it. And then double container with the shock absorbers. So these were transported like this. So this is the transport of along with the purging setup. This is the overall view of the MGK Menon clean room facility. This is the vibration test, and that is the thermovac chamber in eyesight. And this is the integrated AstroSat. So this is the AstroSat transport, and this is the launch on 28th September 2015. This is the UVET engineering team. Some of the pictures. Yeah, so this is what we made during the 10 years of this is one of the galaxies first observed, and it is we also have now better image processing things. I'll tell you about that as well. So this completes the making of UVET video. Yeah, so this is also one picture from, I had requested KP to share some pictures. So KP had shared this picture, so you can see they and Kalamji looking at it in 2010. This is the SXT mirror. So this is also fabricated and then used. So this is also a very unique system. So this is part of another, the other instrument, S60. So this is the entire, so this is the ground checkout happening. One of the things which happened during the integration of UVET was that it has got 3 detectors. One is the far UV, and the 2 tubes, right? One is only for far UV, the other is for NUV and visual. Now you would ask, why do you need 2 telescopes, right? You could have made it into one and could have actually been more sensitive. Can't it be done? So Galaxy is like this. So Galaxy is 1 tube, and you have actually far UV and the near UV. Now the problem with that is far UV is very critical, particularly because if you pass the UV light, the material absorbs. So you can't actually have an absorbing material in between. So far UV has to be reflective. So you have to have reflective surface, and then finally it gets absorbed in the detector. That's when you detect it. But it has to go through filters, so normally we get crystalline filter so that it doesn't absorb. So you can't have an absorbing material. So you can say take the beam and take it, so what Galaxy does is it has a beam splitter, so it splits the far UV to a detector, reflective, and the near UV passes through the medium, so which actually gets less intense and then reaches the detector. So efficiency is less, but you still get NUV. But we also wanted visual because you have other wavelengths. So if you want to look at the sky and what exactly you are looking at, what is the pointing you're doing, you need to get visual to guide you to which part of the sky you're looking at. So visual was a must. So we want 3 channels. You can't have this happen. So decided to have one, particularly for far UV. The other one, the near UV going to reflection, and the visual is through transmission. So that was the configuration which was arrived at, and that is the reason we have twin telescope. It's actually a UV-TT. It's a UV imaging twin telescope. So that's what you can see. And it is also important that when I say far UV, the contamination has to be minimized. So every component was cleaned, and you can also see the purging going on. Till the last minute we had the purging connected, because if any molecule gets into it, the entire efficiency comes down. So the purging has to continue so that even if the contamination comes in, it is flushed out. So that's the idea here. So many of this kind of an instrument was integrated for the first time in the country, in many such cases for the X-ray telescopes as well. But the beauty of it is that everybody took this extremely seriously. Every particular step is taken very cautiously, very carefully, and all the risks were identified and mitigated. The net result is that you actually have a textbook-like instrument working in space, which is actually very, very difficult. So it is very important to go through all the reviews, all the corrections, all the identifying the risks and mitigating and implementing, making sure that it is implemented well.
So that is the learning we have to understand from how this instrument is done and why it has been working and why it was working from the day one as well as continuing to work till now. So moving forward, I was a calibration scientist on it, and I was assigned to actually identify which is the first light instrument, first light object you will look at. So when it was launched, there were some constraints. So when you launch it and it is going through the equatorial orbit, so it has to, if you're looking at an object which is in the night sky, then when you turn around and come back, you will see the bright Earth. So in initial times it cannot do. So what you have to do is you have to take it away from and then come back to the object. Now initially you can't have too many maneuvers done in the object so that they don't get into troubles. So the mission said that you will only look at one place for some time and maneuvering will be done one by one. Because there are 5 instruments you are observing and 5 different kinds of protocols, so too many commands are going, we don't want any complication. So we had to identify an object which is close to northern pole, like the high declination, northern or southern declination. So we had to identify and stick to it for some time. So because it can to reduce the maneuvering. So finally, after a lot of discussions, this object was identified, and this is I was just going through the files when I had to give this talk, so I found this and then I realized that it's a good thing because this is how the doors were opened. You have to opening first door, the second door, and the pointing at that time is this coordinate because the total that the spacecraft will be for the payloads are pointing in this direction. This is the first target. And this was the first image, one of the very few first images. You combine the entire orbit looking at it, what happens is there is a drift. So you will get this drift, but the drift you can see them are all different angles. That's basically because the detectors are mounted at various angles. So at the mounting itself, you have to actually compute what is the relative angle between one detector to the other. So we know from ground and you can actually correct it, and that is how the images are made. Because when you observe it, they are at different angles. So that also is known, and this is the initial first light when we got. This is the detection, just the photon detection from each scan. So this is like each frame. So UVET actually act like a photon counting device. So just to digress, you can take an image by integrating, you're showing the integration, you can put it in your phone, right? You have some integration time you can give. But you can also count the photons. When do you want to count the photons? When the photons are extremely minimal. When you have too many photons, you should not count the photons because there are too many. But when you have only 1 or 2 photons coming in 1 second, 1 photon per second, or maybe 1 photon in 10 seconds, which is very, very small, you have to count that photon. So the technique for counting the photon is generally used in high energy physics as well as in UV. So that is how the photons are detected here, and then except in the visible channel is integration mode. You can see this integration, and this is the photon counting mode, this is the photon counting mode. So this is the first thing to tell you that the detector is alive and the system is functioning. So this is a big relief to get the first light image. So this is how it was done, and so then we moved on to continuous observing, then performance verification up to March 16th, and then guaranteed time, etc., etc. Similar module was done for all the instruments, and the entire calibration was completed by March of 2016. And there was a campaign where all instruments actually proposed a science, one object to observe so that you can do a multi-wavelength science. So that is also done. So NGC 2336 was actually identified as one of the objects for demonstration. And that is the object which actually was the final the image you saw, the spiral galaxy, is actually 2336. And now the image we first made and right now what we made is also very different because the pipeline has been upgraded and we have a better techniques to actually do the drift. You saw the drift there. The efficiency with which you can do the drift correction is much better now, so we are able to get about 1.2 to 1.4 arc-second images. The actual, what was expected was 1.8. So this is a much better resolution, and that's how it goes. So this is how is it UVET functioning now? It is actually the sensitivity, I mean this is the first light object, and these 3 objects are monitored continuously to make sure that the sensitivity is checked. So this object is quite bright. That is what you see, the large photon counts, and this are less, so this in magnitude and this in counts. You can see that. So this is slightly varying because of statistics itself, and then this is quite flat, telling us that this is for first 3 years, and now this paper is out where we have monitored for 9 years, and it's pretty static. So this is another achievement, because the protocols as well as how you observe in space is done in such a way that you can actually preserve it in quite a long period in space as well. So the data is also out. You will be more or less known that it is ISSDC. Now I think it is moved to Pradhan. This is the old system. All the data is public. People can log in and check it and download and work it as well. So what kind of objects are observed from UVIT as well as the other instruments? These are the general kind of studies done, individual galaxies as well as clusters, etc. I would like to tell you a little more about what I do, because I am more familiar with that. And towards the end, I'll also touch upon other science outcomes. So I study star clusters, groups of stars. Stellar groups can be smaller groups like this. We call them as open clusters. The stellar groups can be much big. The very first image I showed you, globular cluster, in optical it looked like this. So it's a very, very crowded place where too many stars there. So I study these two systems basically to study how stars evolve and what kind of phases they go through, and in systems like this what happens to them. And actually I can show you that they help to understand how stars evolve, because these are the two systems, and we normally study stars by what can you look at stars and study. You can't go there and touch it. So how do you study a star? Is you can see this brightness and you can measure its temperature from ground. So can the brightness and temperature just two can give you information? Yes, it can. And if the stars are all together, like everything is together in one place, then what matters is the distance is the same. So the brightness variation is intrinsic, right? Because if something is bright, then it is intrinsically bright, and you need to understand why it is bright and why is it able to make more energy, and is it hot. So that's such a plot. If you make it, you get the color magnitude diagram. And we know that this system is very old, and it's full of low mass stars, even stars with mass less than the sun, and this one has stars more massive than the sun. So the color magnitude diagram is a bit different, but we understand the evolution of stars as a function of mass. So that is the ideal test bed to even test theories and understand stellar evolution. For example, if you look at a young cluster, this is the main sequence where stars convert the hydrogen to helium. At the core, that's how they produce the energy. So after the helium core grows, it becomes a giant. So it leaves the main sequence. Now this happens for main sequence stars at a brighter luminosity, but it becomes fainter in the older stars. So this thing called turn off is a function of age. So once you know it, then you can actually age. It's an age dating. It can tell how old it is. So this is a very important technique. So that is how star clusters are used as calibrators for even isochrones and theories. You also notice that there is a gap. There's stars which are falling here. These are the stars which actually end their lives as white dwarfs, and they have a sequence as well as the white dwarf sequence, which actually grows as they get old. So this is the single stellar revolution, how stars evolve, study, etc. Now you can also see that these are cooler stars over here, and these are hotter stars. So these stars are more bright in the infrared, and these are bright in the ultraviolet. So you can also see that in the ultraviolet, the crowding gets reduced, as I showed earlier. You can actually see the hot stars, pick up the hot stars and identify how the hot stars perform, etc. And that is how UVIT is important. This is again another thing that, as I mentioned, the stars have to evolve off the main sequence and become giants, because that is how the thing functions, because the helium core starts collapsing. It has to become a giant. It cannot escape it. That's what we find. But I would like to bring your attention to stars which actually stay away, like continue to be on the main sequence, though they should be on the red giant. So these stars are called blue stragglers, and people realize in initial phases thought that they are actually not part of the cluster. How can they continue to be on the main sequence? Because according to physics, they should become red giants. But somehow they are evading that evolution. They are trying to stay young. How is it possible? So earlier they were ignored, but then later on people realized that no, they are actually part of the cluster, and they need attention, and either they could be, how are they able to stay young? The only possibility is they are able to get matter from somewhere, where? Most likely a nearby companion. So then you started looking at binary stars. Can they actually eat up the near star or eat up a part of it? So what happens to the system? But do you actually see it? Or as I mentioned earlier, when two stars collide, as I mentioned earlier in some systems, can that collision make these stars? We don't know. We have to go up and look for it. Now, studies regarding this was not very done much, and ultraviolet has played a major role. That is how I would like to tell you more about it. So what happens? How can this be formed? As I mentioned, you have two stars which are nearby, and somehow the A becomes big, and since it has become big, the mass gets transferred to B, and the B actually jumps up its luminosity because it has gained mass, and what happens to it? It will die as a white dwarf probably. So such a system can be here, and this is the main sequence. So some of the stars which are shown here are thought to be evolving stars like this. They don't end up as white dwarfs, but something like this. It was proposed but not really understood. So this is one possibility. Now how do you even go up and find out and convincingly get a story that this is how exactly it's happening, right? So you need to actually see them in a cluster, and can you actually see this? And you should all be able to detect this. So A, B, you probably we see binary stars, but do you see this as kind of systems? Which would mean, do you detect A? B is detected. So we see them in this cluster, right? So we see them here. Do they have companions? Do they have companions like this? That is the question. Now how do you detect them? You can see that the luminosity is very, very low. It's very, very low luminosity, so detection is very difficult. But you can detect them if you go to this. So these hot stars are low mass stars, but they are bright because they are bright in the far UV. So you can actually do this, and so what you do is you can actually measure the multi-wavelength coverage. So you can actually measure the wavelength across the spectrum and find their energy distribution. So if they're hot, you can actually see them pick up in the hot. So you can see this here, this particular part, and you will see the combined one here. So this is the techniques which we used, and this is the first paper from UVIT where you can actually have the cool and the hot together, and then find out that yes, that such systems actually have, are possible. So we went ahead and did a lot of survey, and so we have about 20 publications now, and a lot of community have contributed to it, many PhD theses, etc. Now what do we understand? We suspected them, so this is 100 times the sun's luminosity. They're here, so they're here, but people did not see them, these people here, because this actually continues down up to here, which was not predicted, but we see the entire continuation of here. So what UVIT has opened our eyes is to say that, look guys, there are a lot more of them sitting there as companions, and it is able to understand that many of them have companions. They are also happen to have a sequence here in between our main sequence and the white dwarf sequence. The white dwarf sequence is over here. So these are all, we call it as different types of white dwarfs. It could be low mass white dwarfs, ELM white dwarfs, but all are stripped stars where the outside is stripped off. So that is one thing. Second, we also have, when you actually the stars evolve, do you see them dying? We don't see much of them dying like this in a cluster. This is one very weird case where we actually catch it while it is transferring from the IGB to a white dwarf. So this is the one of the planetary nebulae, and this picture is seen like this only in the UV because this hot ionized gas is picked up. This is also done by a lot of people, and this globular cluster survey is taken, and then you can see that this all the optical images, when you see in the UV, you can see the cores are quite separate. You can see them, you can see the hot stars, and this is also taken up, and lot of papers have come up as well. Going to other fields, so you can, a lot of interesting work is done by the AstroSat ultra deep field. Here also again, this deep field is taken such that you have wavelength coverage, and UV coverage was missing, so ultraviolet coverage is provided by AstroSat, and this is done by Kanak and his students from IIT, and they have found Lyman continuum leakers, and it is one of the major highlights from AstroSat because HST is there, but UV is detected from here. So this is a very interesting result from them. And there's also another one following it up, witnessing the live formation of dwarf galaxies using the ultraviolet eye. So this is an excellent continuation of their work. There's also work on the nearby galaxies where the novae were identified in M31, and this is looking at variables and their distribution. This is from Basu et al., etc. And going to, this is the old supernovae remnant, where this actually you can see this veiling, the remnant, actually the ionized gas is part of this, and this is observed in actually S60 as well as in UVIT. These are UVIT footprints. The entire thing is a galaxy image, and this study is also going on to understand how ionized material is coming out of the supernova remnant. So this is the S60 thing. So in terms of for the X-ray studies, this is like a very exotic systems where you have a neutron star and a black hole. You have accretion material around it, and the kinetic energy, the gravitational energy is converted to kinetic energy, and the energy is converted to heat and gas, and a lot of material is thrown out as well. So you have a combination of a star, black hole, and disk just in this case, and a lot of material coming out of it. So these are variable sources as well. So you have to actually cast them and continuously observe them to find out the physics involved in the accretion as well as how the matter is falling in. And so these X-ray binaries, neutron star X-ray binaries as well as black hole X-ray binaries are main targets for the X-ray telescopes, and these are the ULX pulsars, and these are some of the results coming from a large group of people about the measurement of spin periods and the revolution of observations of several accretion powered pulsars. So these are the sub-Eddington and super-Eddington components. The another cyclotron absorption line in high magnetic field results are also there. So there are a lot of them from combination of LAX-PC and S60 in Hercules X1. And this is the unstable hydrogen and helium burning on the surface of the neutron star, while due to accretion, rapid thermonuclear outbursts. So these outbursts are counted, and LAX-PC has a very excellent timing, so you can actually get the timing and the variations captured very nicely. And X-ray polarization is another achievement from CCTI. So this is the result coincidence with radio emission hints that hard X-rays are from a jet, possibly synchrotron radiation in ordered magnetic field. So this is Chattopadhyay et al. 2024. And the gamma ray bursts, there are so many of them detected from AstroSat CCTI. So this is the distribution of them in the sky. These slides I thank KP for sharing with me. And I would like to summarize by saying that what has it done, and how many publications, what are the type of topics, and so this is the overall distribution. It is continuously getting upgraded and continuously increasing. And I also mentioned that this data which is collected is actually quite of archival value, and more people are using it, and the user numbers are increasing. So this is bound to grow, and you can see many of them. I covered most of them, and I've done a chunk of my contribution to this particular part of it, apart from galaxies as well. So just to summarize, so AstroSat was a very ambitious as well as very successful first space observatory of India, though less publicized. It's produced a huge amount of not only science, but also people who got trained in space instrumentation, how to handle things, engineering team as well as science team. So the large amount of people are trained, large amount of data is produced, and as I mentioned, the payloads have been functional for more than 10 years. There is already a major impact on the scientific landscape. You can see so many students, PhDs produced in India as well, and so many people still using it, and the growing number of people, growing number of papers from the community. The archival data will continue to make an impact at least for next decade. I'm sure for UVIT, because even with this moderate resolution of 1.2, nothing is going to come up in the next 1 decade. So even if missions like UVEX or UltraSat are going to come, if they are of resolution 2 arcsecond and 5 arcsecond. So regions which are observed by UVIT will be of extreme high value. AstroSat will continue to operate till technically feasible. There have been several activities on the follow-up missions. I haven't got slide because I thought I'll run over time, so I didn't do it. But there are many proposals which were submitted based on a call for proposals, as I mentioned, INSYST and Daksha. And INSYST basically is a follow-up based on UVIT and Daksha from the X-ray payloads. we were given, both these proposals were given seed money to actually conduct some technical studies as well as demonstrations, which have been done as well. But as of now, none of the proposals have moved further, but there have been a lot of studies and a lot of proposals based on that. And I hope soon there will be some action to move forward, because the community is still looking forward to new missions. Now that I was introduced as a musician, I must prove that I am right. So I just wanted to make sure that so I've been trying to, I've been playing violin for more than 50 years. I also am interested in various cultural activities as well. And I've played in various TV programs and also in a documentary. So I just play a bit of violin, which is recorded as well. And you can see I also want to culturally integrate. This is a mekhla chadar from Assam. So I hope I'm wearing it not too bad.
Anga.
Yeah, okay. This is part of the documentary which we recorded, so I put that. Yeah, thank you.
Thank you so much, Professor Subramaniam, for taking us on a journey about the construction of the AstroSat, the science it has delivered, the people it has trained, and how it has changed the landscape of how we understand various objects in the sky, from globular clusters to figuring out how blue stragglers got there. The talk is now open for questions. If you have any questions, curiosities, something you would like to know more, please just raise your hand. We'll get a mic to you and you can ask your question. Excuse me.
So, good evening, ma'am, and I appreciate your mekhla chadar. I'm an Assamese, so I'm very proud. I'm feeling very proud that you are wearing this, our cultural attire. So, my question is that how this UV data can be accessible for researcher and the students, how can we get that data?
Yeah, so UV data as well as all the AstroSat data from each of the payloads is actually out in public. So it's already released. So you will get L2 data. I think it is right now sent out from Pradhan website. So you'll have to look at Pradhan website and then register there. And then once you register there, you will have access to all the data. So there's observations when there is the preparatory period, but most of the data is actually completed and it's public, so you can be able to, you are able to download and analyze the data.
Okay, my second question is that how it is different from Hubble telescope?
Yeah, okay. Hubble Space Telescope is a 2.3 meter telescope. It actually has been there for a while, and it looks at the smaller part of the sky, and since it's a bigger mirror, it can see fainter objects. So the field of view is very small. You can do optical imaging mostly. There is a far UV also and UV possible, but very small area of the sky. The UV can see much bigger part of the sky, but it can see only in far UV. We had near UV, the detector got corrupted, so we can't use near UV now, but far UV, we can get a larger part of the sky. So that's the difference.
Thank you, ma'am.
Thank you so much. Any other questions? Yeah. There's a hand at the back there. Yeah. It's not yet on here.
Thank you for very interesting talk. You mentioned about the gamma ray burst observations using AstroSat. So are they the prompt emission observations or they are afterglow?
They observe the gamma ray burst. So you, that is the emission coming from there, right? So that's.
So they happen to be observing when the burst took place.
Yeah.
Right.
Okay,
Where,
because
it's
so this
because it's not like whenever it's pointed to one direction, it can actually collect from a larger part of the sky.
right.
So
So
it actually collects the gamma rays part. Yeah.
okay. So generally, when the prompt emission is in the X-rays or gamma rays, I suppose it is UVIT. So probably the afterglow part. Is that
Afterglow
correct?
part is UVIT, and UVIT is observed in some cases, but what happens is it takes some time for, let's say, target of opportunity observations. It takes a little bit of time for the observatory to change what it is doing and then go to another object. So that is one problem. So in some cases it is observed, but in some cases it's a very immediate observation. It cannot carry it out. Yeah.
Thank you.
Thank you. Other questions or curiosities here?
This one at the back,
Yes, yeah.
to 8th and back.
At the very back, yeah.
So, ma'am, our question was, as the archival data of AstroSat grows, how is advanced deep learning architecture and algorithms used to analyze the data of AstroSat? Like, how is IIA approaching towards it?
Yeah, the first approach is that we have released the science study images, which is the L2, but the UVIT from the POC, we have not yet released the catalogs. So you need to have catalogs as well, but you need images also. Like if you go to Aladdin and you want to overlay, you also along with SDSS, you want to see a UVIT image also. So that also need to be done, and also catalogs, which would be like, point object catalogs, where you don't want to worry about any of this processing, but you would like to put the UV data point of that particular object you care, so to integrate it with rest of it. So you really don't want to go through the processing part. So these are higher level data products. So we are working on it, and we will be releasing some part of it and then continuing to grow, because these archival material is very important, and how you archive it and how you disseminate is also important for visibility. So we are looking into it. LLM comes after you have a large amount of data and what you can do, classification, etc. But we haven't reached that part. But of course, when the field of view is very large, like half a degree field, and your object is only a few arc minutes at the center, you get the entire field of view free. Yeah. Then once you do the processing, you need to classify those objects. So there, of course, it is important. Yeah.
Thank you. Okay. So towards that end, there is a question. Yeah, there's a lady who's standing up. Yeah.
Hello, ma'am. I want to ask: is there any way that we can use AstroSat to use to study the sun?
No. So actually, it's not designed to do that, and UVIT cannot do that at all, because this is it has to look away even for the galactic plane. Not possible. Yeah, it's not designed to do that. Yeah.
Okay, is anyway like indirectly, because sun also emits X-rays that.
So we have Aditya L1 and the mission looking at it. Okay. So there are other ways to look at the sun as well.
Okay, yeah. Thank you.
Thank you for that question. Any others here? So at the back again, yeah.
Hello. Good evening, ma'am. Considering the kind of data that AstroSat collects, what kind of problems can be solved in the domain of accretion physics using the data that is regarding extra binaries, particularly extra binaries, and like accretion physics using the data from AstroSat?
Sudeep is right here. Sudeep, you should catch hold of Sudeep. He would be able to answer you much better than me. I don't work on accretion physics as such.
Yeah, if you could just raise your hand so that he can identify you. Yeah.
Sudeep.
What's the question? Can you please repeat?
Your question was what kind of science can you do regarding accretion physics using AstroSat data?
Oh, okay, all right. So you see that when a compact object like neutron star or black holes or white dwarf, they accrete matter from the companion star or the surrounding medium, the accreted matter or the accretion disk can probe a very close region of the compact object. That region is of very high interest because it is the strong gravity region for neutron star and black hole. Therefore, this matter which emits X-rays, because when it comes very close to the compact star, it emits X-rays and it shows a number of spectral and timing features as well as nowadays also the polarization features. And all these features can be used as a tool to probe the strong gravity region, to measure the properties of the compact objects like the black hole spin, mass, for neutron star also spin and mass, and therefore for neutron star the core matter density is about 5 to 10 times the nuclear density, and that is a fundamental understanding that matter is a fundamental problem of particle physics and astrophysics. So you cannot do this in terrestrial laboratories because this is degenerate matter. You can address all these exotic, extreme, and fundamental problems of physics and astrophysics by studying this accreted matter and accretion disk, as well as the accretion and ejection mechanism in the strong gravity regime you can study. And this accretion ejection is a ubiquitous phenomenon of the universe. Essentially, all the structures of the universe has been created by accretion, matter gathering, the clumping, collapsing, etc. So to understanding this in the extreme environments is what you can achieve by looking into these features, the spectral timing polarization features that come from the very close to the compact object because of this accretion. And that is the answer you.
Thank you, sir.
Thank you so much. Any other questions? Yeah. There's one very close to you, yeah, up there, yeah.
Yeah, I think I'll want to ask a few topics in terms of your experience in terms of being able to operate multiple instruments on the satellite and schedule timing on it. Were there any unique ways of payload planning that came up during the 10 years of mission lifetime, and which allowed, because while working on space instrumentation after my PhD and all, I have been going through these systems design aspects for the satellite and payload operations, etc. So was there a unique thing that came out of multiple instrument observations, each of them requiring a different pointing direction, but still...
So the challenge which was there was that these instruments have different sensitivity, different safety requirements.
Right.
You with the stringent of the safety conditions.
Correct.
So it has to, you have to make sure that the high voltage is lowered and brightness check has to be done, because as when I mentioned, the far UV has to be kept alive but not dead. The detector, photon counting detector has to be alive, because in Galaxy we actually lost it. So severe conditions had to be put, and that had a bearing on the other, because you can't have a multi-wavelength data for those regions. It has to be put off. So and there are cases where it cannot see far UV, but it is X-ray it can see, but then you want to actually get X-ray for a far UV object, it is too faint and it cannot collect. So the sensitivity across was not a match, so you have to actually compromise on how you actually effectively do it and in fact get a reasonably scientifically good data. Apart from that, if your question is regarding how the mission operations were done and how it was controlled, I think I can't answer that question because I am not privy to how the mission actually made sure that, because the there are several conditions with the instrument itself puts, like the ram angle clearance, because UVIT is going like this, then you cannot observe like this, it has to be away because you don't want to scoop out the debris on the way, so it has to be away. So on the orbit it can, from the orbital axis it has to be shifted. So equatorial plane was not able to observe because of this constraint. So everything has its own constraints. So that along with the mission constraints and the momentum dumping, etc., they have to finally make sure that it is observable. So it's a highly complex system. I don't have the entire answer for it. Yeah.
Thank you. Yeah. Okay. Yeah. Please. Yeah.
Yeah. Hi, ma'am. Very nice talk. Thank you for that. I have a naive question. So I was just thinking that you are talking about this evolution of this companion star through this HR diagram, and AstroSat, I presume, came up with this observation or this idea first. I was just wondering why the previous other observations of the globular clusters could not get that thing. Is there some kind of advantage of AstroSat?
Yeah. So one is the we could have done it with Galax. But Galaxy is just 2 filters. Sometimes the crowding is a problem. Galaxy is about 5 arcsecond resolution, and clusters, that is not enough. You can have some companion giving some additional flux, so you can't actually isolate it. So UVIT resolution was very, very critical. That is very important. Apart from that, UVIT also has multiple filters. So as I said, one of the very first publications, we had the measurements from all the filters, 4 from near UV and 4 from far UV. That 8 filters actually gives you a very nice slope in the ultraviolet, which gives you confidence of the flux measured. So that is the resolution, and the multiple filters present in this channels were a unique feature of UVIT, because of which we could actually detect these companions, otherwise not detectable. Yeah.
So while designing this UVIT, this kind of observations, people kept in mind?
Actually blue stragglers was not in the wish list of it, but then there were other things, including which was actually still to be done. If you look at planetary nebulae and you have emission, actually gas, but you can, if you cleverly choose the filter combinations, you can actually isolate which part of the region you're looking in the spectrum, and there will be emission lines, and you can actually see that this is the major contributor of this element in this particular region. So that can be done, but it just I think there are more data available, can be done as such. So that was a cleverly chosen filter system, but there's also constraint, because in UV you can't design the filter, interference filter or something like that. You eventually get a crystalline filter, and eventually the effective area and the wavelength coverage turns out to be something, and you have to live with it. You don't have a choice. We had one very nice filter in UV, which basically turned out to be it is a kind of a wedge kind of a thing, as well as very less throughput, though it was extremely essential to understand the interstellar reddening, so which didn't work. Yeah, so there are issues there as well. Yeah.
Thank you.
Thank you. Yeah. Any other questions? Okay, I don't see any more raised hands, so let's once again thanks Professor Annapurni Subramaniam for a wonderful talk. Yeah. There are a couple of announcements from the LOC. One is that there is tea waiting for us out here, yeah. And the other one is that the vehicle for the nearby hotels, the Sanchita and other hotels which the LOC promised to drop people at, they will leave at 7. Anything else? Okay, thanks. Thank you so much. Thanks for joining us here, and have a wonderful evening. Thanks. Yeah.